the Lagrange density of the SME is constructed from the known fields of our standard physics. That's standard model and general relativity, and then we just add to the theory all possible couplings to Lorentz-Violating coefficients, and like the ones you see here, A and B. And because it's written in terms of these theories that we know how to use, we can calculate with it, and that means we can make predictions for experiments happening at our current energy levels. So the way that I think about it is if there's some underlying theory, say of quantum gravity at a very high energy scale, then the standard model extension is a sort of low energy effective field theory for it. If it includes Lorentz violation, then we know the standard physics obviously applies, and we just use the standard model extension corrections to add on all possible Lorentz violation. And effective field theories have been very successful in explaining low energy effects. For example, the ripples on the surface of water. You don't want to use quantum physics to describe the ripples on the surface of water. You use a field theory. And we know that the solutions to the field theory are built by plane waves. And if we combine the plane waves in certain ways, we can create wave packets. And in quantum field theories, these wave packets follow the classical trajectories of particles. So why do we want to study point particle Lagrangians? We just saw that there's this natural progression from field theories to point particle descriptions. But there's other reasons why we want to study it. First of all, little's known of the kinematics of point particles in these Lorentz-Violating backgrounds. And secondly, and maybe more importantly for today, many experiments involve signals from macroscopic bodies, most notably gravity experiments like LIGO. And macroscopic bodies are much easier to describe using these classical Lagrangians. And then finally, the exact momentum velocity relationship is unknown. So problems like two-body scattering problems are unsolved. Okay, so now the connection to Finsler geometry. And you see a picture of Paul Finsler in the bottom right there, but also a picture of Riemann, since he originally put forth some of these ideas. It should be called Riemann-Finsler geometry, but I will shorten that to Finsler geometry for now. So the point particle Lagrangians represented by the L on the left there, and the Finsler norms, which are central to Finsler geometry, represented on the right. You can see that as functions, they have a lot of the same features. They're both real valued functions on the tangent bundle. They're both smooth and one homogeneous in the velocities. And the metrics take the same form in both cases. There are some major differences, which means that a Lagrangian is not a Finsler norm, but we will come back to those differences later when they become important. Okay, and then to show why the standard model extension and Finsler geometry kind of go together, I have this visual representation of the two things where on the left you see that general relativity is a special case of the standard model extension, and in the same way that Riemann geometry is a special case of Finsler geometry. On the left, we can construct the SME from general relativity by adding perturbative background field couplings. And on the right, we can construct a Finsler geometry from Riemann geometry by adding covector field couplings to the velocities. In constructing point particle Lagrangians, we don't quite get all the way to a Finsler geometry since a Lagrangian is not quite a Finsler norm. So we're left somewhere in the middle here in this kind of no man's land of pseudo Finsler space-time. And the precise definition of this is still an open question, still being researched by quite a few people. And so we can add to our list of why to study point particle Lagrangians that it gives us a lot of more examples of possible Finsler spacetimes. Okay, so we don't want to dwell on this. What we will do later is show that we can come up with a mapping that maps our Lagrangians to true Finsler norms, and then do some geometry with it. There's another link between Finsler geometry and general relativity in the context of Lorentz violation, and that starts with how the Lorentz symmetry is broken from an underlying theory. Symmetries can be broken in two ways in physics. The first way is spontaneous symmetry breaking, in which the underlying theory has Lorentz symmetry, and there are some fields that are dynamical that at low energies acquire backgrounds. They freeze out. You pick a solution and they freeze out and they break Lorentz symmetry. The other possibility is that the underlying theory of quantum gravity, whatever it is, has explicit Lorentz violation. In this case, the background is not dynamical. Lorentz symmetry is broken at all energy levels. And in general relativity, this has implications for the geometry. So to see how that works, you can define the Einstein tensor, just a geometric quantity, and then together with the Bianchi identity, gives you this first condition, actually the trace, gives you the first condition. When you combine that with the Einstein equation, you see that it implies this bottom equation here, which is the kind of a conservation of energy momentum condition. But in the presence of background fields represented by the K, we see that the covariant forward divergence of T is actually non-zero in general. And we have to have a vanishing of the right-hand side to rectify that with the first equation we saw on the previous slide. In the case of spontaneous breaking, there are dynamics that this K field obeys, which we assume satisfies everything and everything works out and the right-hand side will vanish. But in the case of explicit breaking, there's no wiggle room in the background field. There's no degrees of freedom there, no dynamics. And so the extra degrees of freedom to reconcile those requirements must come from some other place. So the idea is maybe that comes from Finsler geometry. And we think that might be true because we can write down a Finsler metric as a Riemannian metric, which depends on the space-time point only, plus some modifications which can also depend on direction. And so it's this direction dependence that gives us the wiggle room in the background to satisfy the requirements we had before. Okay, so now specifically, what scalar field theory did we work with? And probably first, what do I mean by scalars? That's probably not what you're thinking. So in physics, we have a property of particles called spin. There's different kinds of fields, scalars, spinners, vectors. These things are referring to the spin of the particle. In certain cases, the spin can complicate the trajectory. And by scalar, I mean a quantum field which describes spin zero particles. So the reason why these things are nice to work with, besides being easy to work with, a large subset of the Lorentz violation effects are spin independent. And that means that even spinners and vectors might be handled as if they were scalars in the propagation involving these backgrounds. The other reason is because the most general Lorentz-violating scalar field theory hadn't been studied yet. So here's the most general scalar field theory, the one that we're going to use for the rest of the talk. The first two terms are the free propagation of the scalar field phi. It has a mass m. The second two terms involve the Lorentz violation, where the Kc and the Ka have a hat on them. That means that they're actually expansions in the derivatives here. So the first term is the Kc terms that includes all the terms with an even number of derivatives. And the second term, the Ka terms, include all the odd number of derivatives. And the Kc's and Ka's without the hats, those are the ones that are the actual coefficients for Lorentz violation. So we assume that this sum is not infinite. It must be finite at some point in order to get meaningful solutions. But it's arbitrarily large. It's as large as you want it to be. The K's are assumed to have constant Cartesian components. This is to preserve energy momentum conservation. We'll relax that assumption once we get into the Finsler geometry. The N stands for the number of space-time dimensions, which is usually 4 for us, but we want to keep it general for now. And the D is the mass dimension of the operator. So this is important for the rest of the talk. I'll mention the D's as we go on. So the unit system that we're using is called natural units. That means everything is written in units of energy or mass. And so we can characterize the different coefficients for Lorentz violation by their mass dimension, what the mass dimension of the operator is that they're multiplying. If you want an easy way to remember, the mass dimension -2 is the number of derivatives that it couples to. So a lot of work has been done in the minimal sector. I should have mentioned the word minimal before. Minimal means mass dimension n or n-1. So and the rest of the terms are called non-minimal. It's because they're the smallest terms in these expansions here. The d equals n and the d equals n-1 are the first terms. So those are called minimal. So a lot of work has been done here, as you can see, over the last 20 years. But all of it has been in 4 space-time dimensions for the minimal coefficients, d equals 3 and 4. Recently, in this 2018 paper at the bottom, there's been work for the non-minimal term d equals 6, but no results so far outside of 4 space-time dimensions, and the rest of the non-minimal sector has been ignored. And this is a shame because only the d greater than n can actually be observed for a scalar field. We can see that from the top here. If you look at the d equals n term, that's the Kc hat with no extra derivatives. And this, of course, can be eliminated by a change of coordinates, which just changes your background metric. And then the d equals n-1 can be eliminated using a phase redefinition of what you mean by the field phi. So only the d greater than n can actually be observed for a single scalar field. So a lot of the work on what is observable hasn't actually been done yet. We can also see from more general field redefinitions that the coefficients can be taken to be traceless, and the commutativity of the derivatives means that they can be taken to be symmetric in all their indices. For the physicists out there, if there are any, in 4 space-time dimensions, your Kc is the CPT even terms, the Ka is the CPT odd terms. CPT is just the discrete symmetry of nature that's tied to Lorentz symmetry. And then the last term there for Hermitian fields becomes a total derivative, and so doesn't contribute to the action, and that means that Hermitian fields can't violate CPT. Okay, so if we vary the action, then we can get the equations of motion, which look like this, and then plugging in plane wave solutions gives us a dispersion relation, and our normal dispersion relation for a relativistic field is just p squared equals m squared. So you can see the Lorentz violation is affecting the propagation here. These p's we call momentum, by the way. These are just the wave vectors for the plane waves. for the plane wave solutions. So this is the constraint on the wave vectors of the plane waves that gives you plane waves that satisfy the equation of motion up at the top. Okay, so now that we've got our scalar fields done, we want to know how do we construct point particle Lagrangians. This will get us almost the way to Finsler geometries. So it starts from the dispersion relation, and it starts by recognizing there's two ways to view this thing. First is a constraint on the wave vectors for the plane wave solutions, but the other way is a constraint on the momentum of a point particle. So we want to answer the question, what kind of point particle Lagrangian would generate this dispersion relation? So the formalism for this was set out in the paper at the bottom there in 2010 by Neil Russell and Alan Kosteleski. It starts with the dispersion relation as one of our conditions. And then we, as I alluded to before, we can think about a wave packet built by plane waves that follows the classical trajectory of a point particle. And so we can enforce that condition by these n-1 equations in the middle there. And then finally, we want the action to be invariant under reparameterization of the path, and this forces the Lagrangian to be one homogeneous in velocity. So together with Euler's theorem on homogeneous functions, we get the form of the Lagrangian shown at the bottom there. So the idea then is to take these middle n equations and eliminate the components of the momentum, the p's, and then in principle that lets us write L as a function of u, and this is what we want. But unfortunately, this is very difficult in general, and we've only been able to do it exactly for certain quadratic and quartic dispersions.
You're solving the inverse problem.
Yeah.
Mathematics.
Yeah, that's right.
Okay, in mathematics we have similar problems that given the geodesics, how do we reconstruct the metric?
Right.
So that the geodesics of the metric is the same as
Right. Yeah, it's
the same size.
It's
in physics you just reconstruct, trying to construct the metric and give this property.
right, exactly.
It's hard.
Yeah.
Inverse problems.
Yeah, it's hard, and the reason in this situation, the reason that makes it so much harder is that is that for the higher mass dimension coefficients, they couple to more and more powers of p. So you end up with for just the first non-minimal term, you end up with a quintic in the momentum that you have to solve. And of course, not all of the solutions are actually physical solutions. And the higher mass dimension adds a power of p every time. And so, so this formalism has actually been applied to certain limits of the SME, where I said some of the exact Lagrangians have been found for minimal coefficients. In 2018, Rees and Schreck got a ansatz method for the fermion sector. These are spinors, so these are spin 1/2 fields that describe things like electrons. And they got first order results for non-minimal coefficients. And we'll show you a new method which generates all orders for the minimal and non-minimal terms. So here's the way to find the exact Lagrangian for d equals n. These steps become important later. So we write down the dispersion relation, like you can see here at the top, just introducing this quantity omega. And then taking a derivative with respect to pj gives us this equation here when we use the group velocity, classical velocity identification. And then multiplying through by pj again, and using some more of those equations I showed before gives you this momentum velocity relationship. So now we can invert omega and multiply through by a u, and this actually gives us a quadratic in L, where we can solve for the exact L, which is shown here. And this matches the previous results from 2010. And as I was saying before, for d greater than n, there's extra p dependence. There's more powers of the momentum that show up, and so that makes this solution much more difficult. And so we can follow the previous steps that I just showed you to get a quadratic in L, which we can expand in powers of k to get this big mess you see here. So this thing is ugly, obviously. It has p's everywhere, and I said we wanted to eliminate all the p's, so it doesn't look like we did anything good. But this equation actually becomes the starting point for an iteration procedure, which lets us generate L to any order we want in K. So how that works is we first take the limit of L for vanishing K, and this gives us our 0th order Lagrangian, this mu shown at the bottom. This is the normal one for relativistic particle. We can then get the canonical momentum by doing the derivative of L, and this gives us our 0th order momentum. And then we take that 0th order momentum and plug it back into the series expansion I showed, that big mess, and keep to 1st order in K. And this gives us our 1st order Lagrangian. So that looks like this thing here at the bottom. And then we can take a derivative to get the 1st order momentum, plug it back into the series expansion, and keep going to get as high order as you want in the background. I should mention that this equation then is assuming only one k is non-vanishing, so we just took one of the k's for kd here. These are not hats, they're tildes. So this is just one non-zero k. And the k tildes will show up again. That just means that it's contracted with the unit velocity as many times as necessary. And this matches the previous results from this ansatz method I mentioned for the fermions. The first two terms there, the 1 minus 1/2 k tilde is what was obtained in that paper. And it matches those results for the spin-independent part, which is what we expected, that these fermions can be handled by scalars. Okay, so finally, let's get some Finsler spaces. We've got most of the way there by constructing a point particle Lagrangian, but we want to get all the way to a Finsler space, so we want to use a mapping to get from our Finsler space times to true Finsler spaces. And so we want to keep in mind that the main differences between the two functions, first is that the Finsler norm is non-negative, and secondly, that it's a convex function, meaning the metric is positive definite. So what do I mean by analytic continuation? A simple example here is a two-dimensional Minkowski space-time where you have the line element shown on the left. You make this kind of mapping here to these prime coordinates, and when you get the new line element in terms of these prime coordinates, you get a Euclidean metric. So that's the idea. And this has been applied to other SME-based Lagrangians. Here's the AB, the so-called AB space, where the vanishing B gives us a Randers metric, where you can see the Euclidean norms modified by parallel projection of Y onto the background. And the vanishing A gives us a so-called B space. And then some more bipartite norms were studied that include A and B space, and also spaces generated from the H coefficients. These were generated for the in spaces, in dimensional spaces. And at the end of this paper, at the bottom, this 2012 paper, there was this really nice isomorphism structure between the different spaces for different n and different number of indices, different ranked objects. So how our map works is shown here. You can apply this map to any of the Lagrangians you get, and it gives you a Finsler norm. The idea was to start with the k's and the u's. The velocities are the u's, and the K's are the background fields, and apply this map, and then the P and the L must transform for consistency in the way that you see there. I to the power of n stands for the imaginary unit I raised to the power n, where n is the number of space-like indices present in the quantity before the mapping. So this thing will give us a non-negative Finsler norm, takes our background Minkowski metric to a Euclidean one, and allows ultimately for a positive definite Finsler metric. So we take this map, we apply it to our series expansion. We can generate the Finsler norm using the same iterative procedure, and then we promote the backgrounds, the K's, and the Euclidean metric to have space-time dependence to allow for curvature. So on the left here is an example of that for the first order Lagrangian, keeping all of the different mass dimension K coefficients in there. But of course, this thing you can see is reversible if and only if the KAs are all 0. Those are the odd, the ones with the odd number of indices. And in general, we found that the reversibility of a Finsler norm corresponds to CPT invariance in the effective field theory for n equals 4. And this is a theme that actually shows up in the interplay between Finsler geometry and field theories. So what we've done here is generate an infinite number, really, of Finsler spaces. So the top is we pick out 2 specific Ks and take it to first order. That gives us the F1 at the top. If we were to use that map I showed on the third order Lagrangian that we had before, it would give us the so-called F3 in the middle there. And then at the bottom left is maybe the easiest one to consider, is we keep a single K and we expand to only first order, and that gives us this thing down here. So just to remind you, the K tilde D is a D minus N rank object, so it has D minus N indices, is what I mean, contracted with the unit velocity y hats. So that's the one, the F1D at the bottom left is the one we'll use in the rest of the talk. So this includes Randers, as we'll see in a minute, and you can think about it as a generalization of these alpha beta. We'll give a generalization of these alpha beta metrics, where instead of a rank 1, a 1 index object for beta, we can now use any number of indices here. And every Finsler norm that we generate in this way will be a perturbation of Riemann geometry, and that just comes from the fact that the SME is a perturbation of general relativity. Okay, so the first object that we looked at was the Hilbert form. This is what physicists would call the momentum for mass. So the P is the momentum here. It's the components of the Hilbert form. This is, the normal one is the y hat that you can see there. So it's been rescaled by this K tilde term that's a direction dependent term. And then it's also modified by this direction dependent covector K tilde sub I. So what we get is that in general, the velocity and the momentum are not aligned. This is a common feature of Lorentz-Violating. The next thing we looked at was the metric. So the Finsler metric associated with our F1 looks like this. The RJK is the usual Riemannian metric, and then we have the direction-dependent stuff afterwards. Yeah, looking at this metric, we were able to get a sufficient condition for a positive definite G, and that was not placed a constraint on the maximum size of the components of the Ks. But for any N and D, you can always find a K. You can always find small enough value for the maximum components of K that allows for a positive definite G. So you can see that the first 2 terms disappear for the in D equals N case, and the last term is not direction dependent in that case, and that means that it can be reabsorbed into the RJK, and it's just a Riemannian metric. The same thing happens for D equals N minus 2, except now it's the last two terms that are that vanish, and we just get a rescaling of R. So this is also a Riemannian metric. What might not be so obvious is for D equals N minus 1, the last term disappears and we reproduce a Randers metric, the first order Randers metric. And so we want to know if we've generated any other Riemannian or Randers spaces. So we want to use some theorems that we know about already that tell us, first of all, that a vanishing Cartan torsion gives us a Riemannian metric. And then secondly, a vanishing Matsumoto torsion gives us a Randers metric. And we calculated these, and this is actually the mean Cartan torsion shown here. But you can see it vanishes for D equals N and D equals N minus 2. And we checked it also vanishes for in one dimension as well. It's just a curve.
But yeah, I did the mean Cartan torsion.
Right.
That mean Cartan torsion, in general, when it's vanishing, that might imply that vanish. Okay. Of course, that's for certain special measure. Only works for positive, definite, regular, all the direction. Okay. Then there's a theorem in Cartan torsion vanishes, implies the metric Riemannian.
Okay.
Yeah, but otherwise, some of you have examples. I remember mean Cartan torsion vanishes, but singular Finsler measurement is not Riemannian.
Okay.
Yeah, pretty sure that cannot be regular. I'm talking positive there.
Yeah.
So if a pseudo-metric, so you have to use the force-free index torsion to characterize.
Yeah. And
you can take a quick look,
yeah.
When is the mean Cartan torsion vanished.
Right.
Okay.
Yeah, so we calculated that the one that I actually calculated, it's in the paper, is the Cartan torsion. That one's the one in the paper.
Yeah.
It vanishes as well.
Yeah.
I included this one because it's the Dickey theorem.
Yeah, but that was the condition.
Okay.
So must be positive, definite.
Right.
It's regular in all the directions. You cannot be single in some direction.
Okay.
Then there was a very genius proof in mathematics, maximum principles, Laplace operators. Okay.
Okay.
Yeah.
Okay. And then for the Matsumoto torsion shown at the bottom, it vanishes for D equals N minus 1. The good thing was that these didn't vanish for D greater than N. And so we expect that they're not Riemannian or Randers. So here's the geodesic equation. We wanted to look at geodesics. And the GJ is the spray coefficients. We calculated those, which had the form here. And this is calculated in a funny way, and it's for a physical reason that we did this. But the tildes here, the gamma tilde is the Christoffel symbol for RJK. The D tildes are the covariant derivatives compatible with RJK, meaning D tilde of R is 0. So there's a reason we did this, but the main idea here is that it has the form of what you would normally get in a Riemannian case, and then stuff that depends on the covariant derivative of the background. Okay, and shown here then is a new kind of derivative where you can use this to define some other forms, some other connection forms. Shown at the bottom, we use this derivative to get the Chern connection, which has the form written here. And we calculated the Chern connection to have this form, where again this gamma tilde then would be the Levi-Civita connection, and the rest of the stuff is just depends on covariant derivatives of the background. And so if we remember back to the way that symmetry breaking occurs in the physics, we mentioned that explicit Lorentz violation was incompatible in general with Riemann geometry and general relativity. And what we had there was that we needed the covariant derivative of the background to vanish in order to be consistent. And here we see that if the covariant derivative of the background vanishes, we get the usual results for the spray coefficients and the connection. And so what we know here is that the geodesics are unaffected. And then we actually calculated the Burwald connection and the Burwald HV curvature, and found that it was 0 in that case, and we know now that the spaces are Burwald. So this is the motivation of why we wrote things in terms of these d tildes. Okay, so finally, what are some open questions of future direction of everything here? So first, what we did was we know how to write down quantum field theories in flat space-time with Lorentz violation. And what we've done is to show that we can go from those to a classical point-particle description in flat space-time. And these give us Finsler geometries. What we can also think about doing, though, is writing down quantum field theories in curved space-time using Fierbeins and spin connections and so on. But the harder question then is what goes in this bottom right corner? How do you write down a classical point-particle description in curved space-time that includes Lorentz violation? What we showed, though, was that these exact Lagrangians, the one specifically we showed is up here, but there were others I mentioned. Those are not the ones that we've shown in this talk. So we know that there's other exact Lagrangians that are not.
The Lagrangian here means don't have a
Lagrangians are one homogeneous. Yeah. Yeah, but they're not. They can be negative, and they can be. The metrics are not positive definite. But they can be
not necessarily positive definite.
So they can be they're not smooth on a certain surface, right? And
that's
then
okay.
And then they're not positive definite.
That's okay, but in general, Lagrangians, without the information, without the issue.
Mm-hmm.
But then people can add one more direction, make it still.
Yeah.
Right?
Okay.
Yeah, that's the way. So the geodesics will be, geodesics at Lagrangian will be quite different, because if it has a homogeneous condition, then the geodesic in the direction y and the geodesic in the direction lambda y, there should be the same geodesic as the orbit.
Yeah. Okay.
But if the original measure does not have a homogeneous condition like Lagrangian, then the geodesic in the direction y emission during y will be different. Geodesic with direction lambda y, change the direction, because when coming out, they're not going to go around the same orbit.
Mm-hmm.
That's the difference. So in Lagrangian in general.
Okay.
Yeah, this with a homogeneous condition, we usually just call it still Finsler, but it's in a generalized sense.
Yeah. Yeah.
It's not necessarily, positive definite.
Mm-hmm.
It's not necessarily regular.
Yeah.
Okay.
Okay. Yeah. All right. So let's also mention on this slide that the Finsler spaces that we generated, there's some limit of them that should be associated in the sense that we've mentioned here with the Lagrangians. If there are these exact Lagrangians, if you could find them. should be associated with these Finsler spaces. Okay, and then the other question is a little bit of what we were just talking about. What's a good definition for a Finsler space-time? Exactly, what conditions can you relax and in what ways, in such a way to include all of the different examples that may arise in physical situations. So I also mentioned at the end there that this condition of the backgrounds being covariantly constant, which we call R parallel, gave us Burwald spaces and also the usual geodesics. And these are conjectures related to the SME-based spaces that are supported by what we've done, but still remain unproved. So we note that the R parallel backgrounds are undetectable by geodesic motion, just the free fall of a particle. And so the question is, can the R parallel components be removed from the field theory using coordinate redefinitions or field redefinitions? Okay, and then central to the connection between the field theories and the point particles were the dispersion relations. And these things arise in a lot of different cases and other limits of the SME and other Lorentz-Violating models, but also in physical systems like in optics and condensed matter. And here the question is, can we use some of the methods that we've developed to describe these systems in a geometric way? And related to that is, of course, are there applications to the for the Finsler geometries that we've written down? Are there ways to use their geodesics to describe solutions to certain problems? And so we know that the Randers geometry was used by Professor Shen in a generalization of Zermelo navigation, but also Foster and Leinert showed that B-space geodesics can be used to describe certain physical situations as well. So what about the new spaces we've written down here? And then we're talking about the Dickey theorem, which says that the vanishing Cartan torsion, along with some other assumptions, identifies a Riemann metric. And then the Matsumoto-Horjo theorem says that the vanishing Matsumoto torsion identifies a Randers metric. But in the absence of those two things, is there some quantity that can characterize the B-space or the K-space metrics? So this is an open question I would very much like to know the answer to. And we are getting a little bit short on time, so I think I'll just put up my summary and thank everybody for listening and ask if there's any questions.
Wow. Do you have any questions?
I have a question.
When you talk about the metric, we are more interested in the metric you come up with called K-space, right? The metric. So the Ka theta, how does it look like? It's constant, or you say when equals n minus 3, you get a random metric. Otherwise, in general, it's not.
Let me see if I can find that slide.
Top, five slides back. Yeah, it's a little bit late. Yeah. Yeah, you're talking about the metrics.
Yes. So this one here. So this K tilde.
Yeah.
Put this back up. So the K tilde is the K, which can depend on the point in the manifold.
So it's a function of position.
Of position, but then it's contracted with the direction.
Okay, so it is homogeneous one function. And it's contracted with direction.
Yeah. So the D. So the K has, you can, I wish I could draw. So the K has a D minus N indice. And if it has no indices shown up here, then it's contracted with the direction D minus N times.
Okay.
So it could have, for, let's say, 4 space-time dimensions, for the D equals A term, that K tilde would be K contracted with 4 powers of the velocity.
Okay, portions. Okay, so when you use the notation Yj height, so that's also the homogeneous one when Yj divided by
Y, the magnitude Y.
Okay, so it's homogeneous degree 0.
0.
Yeah.
Okay.
So if D is not equal to N, not equal to N minus 1, what kind type of metric look like? You say it's just I don't have a name for that?
I don't know. Case metric.
I see.
I don't know. You tell me. For D equals N, we know it's Riemannian. For D equals N minus 1, it's Randers. It's not an alpha beta metric because the betas are 1 index.
Yeah.
So I don't know. I've never seen this before.
But it's still computable in some sense.
Yeah. Right.
Right.
So we think that these are new. So we named them K spaces.
But this N is a dimensional space, or usually typically mathematics always need a dimensional space.
Yeah, N is the dimension of the space.
Okay.
So you can pick a dimension in whatever dimension you want, and then the D is the mass dimension of the K. So so it kind of sets the number of indices that you have. And this, I should also mention that this is only the metric associated with the F1 there at the bottom. You could have done this calculation for the F3 or the F1 with 2 coefficients.
It's more complicated.
Yeah, it's more complicated, but you can do it. You just square it and take derivatives. So you can definitely do it. The hardest part is finding the L. So it's not always easy to find. Like you can't take 2 Ks and get that F1. You can't get it in second order because there starts to be mixing between the Ks. And you can do it, but the calculation becomes more and more difficult as you do it.
Okay.
But once you get the L, you can get a Finsler space associated with it using that map.
Yeah. As a mathematician, we already spend a lot of time to study alphabet metric or general alphabet metric, because those are much easier computable, But most important metrics, of course, the random metric, but that also can be viewed as like coming from navigation problem, right? Because it has a direction, the force, additional force of impact.
Right.
Okay, so it's similar to here. You have a Lorentz-Violating, right? So the question: how do you put this impact into the new metric?
Yeah.
Okay. So I did not fully understand this. Alan, created this called the B metric. So to me, it's like an artificial add something like that. Okay. More nature, like a random metric, the navigation form. It's quite much more natural. Understand? See, instead of adding beta to alpha, the point is, if origin metric is alpha, right? You cannot simply add beta. That's the additional force acting, right? We get a metric is that it involves square root of this. Still, it's alpha beta form, but the original metric could be not just alpha. It's already in the formulas we call navigation form. Okay,
Yeah.
so it's not like a direct add something to the original metric
Right.
to create a new metric because of there was an impact from right. So when I look at 30 years ago, when I look at this B metric, first of all, it's a bad metric from geometry point of view. Okay, some direction singular definitely.
Yeah.
And it still looks like to me it's pretty artificial.
Yeah.
Yeah. If you create a new metric and similar to the navigation problem, then there will be living. You come up with the metric, the alpha beta form, alpha plus beta, but it's alpha is not the origin. Alpha.
Yeah. The B term originates from a coupling to the spin in the physics, and so that makes the physical interpretation in terms of geometry not clear. But in this case, these are not. There's no spin here, and so there should be some geometric problem for which these can be applied. Right?
Yeah.
These should be just like physical particle, just like a ball. It has no weird physical quantity associated with it. It's just like, let's say, a ball, and it's traveling on, I don't know, a surface that has some weird friction properties or something. There must be some kind of way to interpret these things.
Okay. Yeah. Okay. I would like to see.
Right now, the interpretation is a little bit different than we use.
Yeah. I would like to see some formula for this type of matrix. How does it look like? We can generalize a little bit because sometimes very specific, right? Like you can say it's like alpha beta form. They only have to use two levels, alpha and beta, right? Describe. Then we do the computation. Mathematicians going to study their geometric property. This is a matrix in this type of form. Of course, you can apply to the very more specific metric, right? So right now they are still a little bit confused. I guess I'm confused about the expression of the metric presented. The notation. I know physics we prefer like K, theta, and the D on the side.
Yeah, we ran out of symbols eventually.
You ran out of symbols. So if someone who really interested to look for a new type of matrix and study it, other than the alpha beta matrix, this probably those type of matrices probably be a good candidate because at least some like a physical background.
Yeah.
It's not that artificial creating.
Yeah.
And okay, that sounds good. Yeah.
Excuse me?
Yeah, do you have questions?
May I have a question? So I connected the internet some minutes later, so maybe I missed something. I want to ask that when you set a metric for the space-time, so how to solve the problem on the differential? Because we know that metric most of the time should be differentiable. So when we consider the space-time, so we lose positivity. So when we lose positivity, maybe the differentiable, how to say it? Maybe the metric is not differentiable at some points.
Right. Yeah. So these metrics are differentiable at all points. If you get the metric associated with L, the Lagrangian, then there are there's a larger slit in the tangent bundle in which the metrics are not differentiable.
So that means that we only choose a part of the tangent space, right?
Yeah, for L, there's a slit other than the zero vector. on which the Lagrangian is smooth. The Finsler norms that we've written here, the F, are actually smooth everywhere y is non-zero.
Yes. Okay, so I'm not sure that in space-time this is possible. At some the direction, the metric is not differentiable.
That's right. Yeah. For the Lagrangians, we know that we get this non-smooth behavior on what we call the light cone. That's
I didn't see the time involved in the metric. It's not the metric, right?
No, the F metrics are not. Right.
It's not.
Yeah. But you can get a metric that's associated with the Lagrangian.
Okay.
And if you do that, then it's not positive definite. There's places where it's singular.
You know, we're talking about space-time, so where's the time direction?
The time is the negative time.
Okay, thank you.
Time.
Yeah.
In the metric, I didn't see it.
Yeah, I mean,
You see the system with d squared minus dx, right?
yeah.
And
Right.
where's the
But this is the metric. This is the Finsler metric, and so we don't have that anymore.
The space.
This is the space. Yeah.
okay?
If we were to take two derivatives of the Lagrangian that we wrote down before, then it would have places where it was singular, it would have a negative.
Oh.
But we didn't want to do that. We didn't want to deal with all those problems. So yeah.
All right, maybe we go back to the first couple slides because I did not record it. So let's see. What is the first 5 slides? People did not see it. Let's quickly go to the first 5 slides.
Right here.
Where's the first one?
Okay, thank you.
Yeah.
Yeah, this was the title, which was Finsler geometry and Lorentz-Violating field theories, and then the overview was the structure of the talk, and introduction to Lorentz symmetry, Lorentz violation, and so here was the experiment I talked about, the Michelson-Morley experiment, where they were looking for direction-dependent effects in the violation.
1887.
Yeah. Yeah, pre-Einstein, pre-relativity. So they were looking for changes in the velocity of light with direction. So this whole apparatus rotated on a bed of liquid mercury, believe it or not. And then we talked about the difference between a coordinate transformation on the left here and a particle transformation on the right. And so this is important in studying Lorentz violation, the difference between the two, and how these transformations are implemented at the level of the physical equations, the physical laws is important. We need to understand that. And so the idea was if you introduce a background and an observable quantity u, this is the energy, and we do a coordinate transformation, there's no change in the observable quantity, of course. The coordinates are just made up in our heads, so rotating a coordinate system doesn't change anything physical. So what you have to do is rotate the physical system and look for changes in the observable quantity u. So that's how we detect Lorentz violation. And in practice, this happens because it's a lab on the surface of the Earth, and as the Earth rotates through one of these backgrounds, the orientation of the lab changes with respect to the background, and we get a signal like you see here, where the energy of some system is oscillating with time throughout the day.
Okay. Yeah.
One more.
This kind of picture very similar to our discussing the navigation problems.
Yeah. Yeah.
We have you heard about, right? So.
Yeah. And we generally take these backgrounds to be constant like this, but of course we don't expect that they're truly constant.
Yeah, that's right.
This Because backgrounds can move around and have whatever behavior you want. We're just looking for the average value, so we picture the average value as some constant in the vicinity there.
Okay. Cool. Let's stop here.